Today we're going to talk about external memory data structures. So these are data structures that are designed to recognize the fact that the normal model of computers that we think of is maybe a little bit idealistic. So we usually work in the RAM model or the von Neumann model of computation, where there's a memory and a CPU. You access individual words of memory and you compute on them on the CPU, which is already a bit of a, well, it's not even a bit, it's a big oversimplification of what computers really look like. And when things get really big, you may have data that you want to work with that doesn't live in memory. So it's either too big to fit in memory, so it ends up having to go onto a disk, or maybe it's not too big to fit in memory, you could squeeze it in, but you have an application that you would like to behave nicely. And so, although you have 16 gigabytes of memory available, if you have just one application that isn't doing that, isn't used that much, it would be a shame if that application is using all 16 gigabytes of memory for, I don't know, for storing a binary search tree or something. So external memory structures are designed specifically to store stuff on disks. And how is that different than, let's say, storing stuff in memory? Well, the difference is disks are a lot slower. So it takes many orders of magnitude longer to retrieve a piece of data from a disk than it does to retrieve it from main memory. But so that's the downside, is there's what's called latency in accessing a disk, which is how long it takes from the time the CPU asks for a particular byte till the time it's available to compute with. That's big, much bigger than memory. But to make up for this, and on the positive side, is that we imagine a disk looking like this. And this can either be a spinning disk, a pile of rust that's spinning around and something is reading off it, or it can be a solid state disk. Both of these do this. When you ask for a particular byte or a particular word off a disk, well, what happens is the disk hardware doesn't just read that particular byte or that particular word, it has to read a whole block. So even if you just wanted one thing, well, what has to happen is a whole block gets read, and that whole block gets transferred into memory. Okay? So it's not any cheaper to ask for one byte than it is to ask for an entire block. Okay, and these external memory models, they're usually parameterized by a block size called B. And once you start working in this world, you quickly realize actually the most expensive thing that happens here in this model is this retrieving blocks from the disk. Okay. So you would like to minimize in any interaction, sort of in anything your data structure does, you would like to do it by retrieving the smallest number of possible blocks from the disk. Okay, and that's not even nowadays. That's not even true just for disks. That's even true for memory. So the lessons that we'll take out of this today, they actually hold, even if you're never really interested in really working on data that's on disks. Memory is kind of organized this way too. When you ask for a particular word or particular byte in memory, you don't just get one word or one byte. What happens is a whole cache line gets read into a cache, and a cache line has a particular size. That would be this value b that we're talking about. Okay. So for us, b is going to be the number of, I'm going to put it in quote, things we can store in one disk block. And we're going to look at the usual classic data structures problem, which is storing a sorted set so that you can add things, remove things, and find things. And when I say find, I mean either find the value if it's stored in the set, or if it's not stored in the set, find the smallest value, which is larger than it. So things, these would be the keys or numbers that we want to store. Okay. So I'll probably just say numbers from this point on, and right. So a block B can store B numbers. Okay. So before we build, before we even talk about designing a data structure, well, we would like to know how well we can do. So how efficient, how fast we could hope for something like this to be. And so, well, we could start with the most obvious thing. So here's one solution. Just use whatever, a binary search tree. And store one node in each block. Okay, so you can imagine this. I mean, we have our favorite binary search trees. I guess trees are the favorite one in this course. So you store one node in each block. So you can picture it like this. Remember, binary search tree node has a value x, and then a couple of pointers to the left child and right child, maybe a pointer up to the parent. That's only 4 things. One of them is the kind of number we want to store. The other ones are pointers. So, you know, if B is big, and typically it is, then there's no problem storing one node in a block like this. And then you just do, you know, your favorite binary search tree implementation, and you get that you can add, remove, and search in O of log n, I'll say input-output operations per operation. So if I do a search in my binary search tree, then first thing I have to do is read the root from the disk, decide whether to go left or right. Then I have to read the left child or the right child from the disk that's in a different block. Then I have to read the left child or the right child, and so on. So following a path, each node in the path lives on a block in the disk. So certainly you can do whatever you can do in internal memory, you can do in this external memory model. But the difference is now you're counting the number of disk accesses. So the question is, well, can you do better? I mean, these disks are slow. These IOs are slow compared to other computations. So you like to make them as small as possible, minimize them as much as possible. And okay, so this is a solution, but is it a good solution? And probably not. So I guess the first thing I could ask is, well, how much could we possibly hope to speed this up? I mean, how could we do better than this? Well, I've told you that in one I/O, so reading one thing from a disk, you get B items. And well, we kind of talked about how log n is the best you can do if you're searching using comparison-based data structures. So maybe if you organize things really nicely, then you could instead of log n here, you could get log n divided by b. That would be great. What would that look like in terms of a binary search tree? Well, that would mean that you should be able to follow a path in a binary search tree, maybe like this path here, and like the first B nodes on that path, they would all be in one disk block, and the next B nodes on that path would all be in the second disk block, and so on. And if you could do that, then your tree, which normally has height log n, well, it still has height log n, would mean that you could follow such a search path in log n over b operations. Now, does anybody see an obvious reason, or it's not an obvious reason, but a difficulty in making this work? So is there some reason that this might be difficult to achieve, something that fast?
There would only be one path. So for example, from the root, there could only be one path of length b that's all in one block.
Yeah.
So potentially.
Yeah. So the problem is, okay, so my search is going to start at the root, and well, that means, well, the search is going to start by reading some block. And if I want the search to be able to even begin, that block should contain the root. So it should be a block containing the root. And sure, that could contain the root and some path of B elements. But the problem is, as soon as I compare the thing that I'm searching for to the root, well, there's two possibilities. The thing that I'm searching for could be bigger than or less than. And if I'm only storing one path here, well, that means it's only going to store one of those two possibilities. So if this is the path that I store, and I search for something bigger than the root, well, then the next node I need is this one, and it's not in this block that I just read. So that's that would be great if we could get this log n over b, but somehow it looks really difficult. And we can actually convince ourselves of that, again, using, well, at least for comparison-based data structures, using information theory again. So just think about what happens when I do a search for some value x. So the data structure has to begin somewhere so it doesn't have anything in memory at this point. So it reads some block. I mean, the first thing before it can do anything interesting, it has to read a block with b values in it. Okay. And I don't care what those values are. I don't know, let's call them x1, x2, x3, up to xb. And I don't care what order that they're stored in. If I look at the relationship between x and these numbers that are stored in this first block that I read, there's only b plus 1 possibilities, right? Either x is smaller than all of them. Well, let's say x is not in structure, so it's not here. In fact, otherwise there's even more possibilities. But X could be smaller than all of them, or it could be larger than the smallest one, but smaller than the other b minus 1 of them. Or it could be larger than the smallest 2, but smaller than the other b minus 2 of them, and so on. Or it could be larger than all of them. So, okay, so that's b plus 1 possible ways in which X can fit into this, whatever these numbers that we stored here. So it doesn't matter what we put here or how we store them for fixed X, if all we do is compare it to these things, there's only b plus 1 possible outcomes. All right. So that suggests that, well, we could quickly formalize this into an encoding scheme. So that basically says, well, now look what happens when we do a search. We read a block, we do some comparisons with X and the elements in the block, but we know there's only b plus 1 possible outcomes for those comparisons. And then based on those outcomes, we read another block. And then same thing, we compare X to everything in there. Based on those things, we read another block. And so on, until eventually the algorithm finishes and says, okay, now I know where X fits into to the entire sorted set of numbers that I have. So, you know, if I'm storing n numbers, that means those numbers break the real line up into n plus 1 intervals. So let's say the numbers were z1 to zn. And by doing this search, I figure out exactly where this number X that I'm searching for, which of these n plus 1 intervals it lies in. And each block that I read only reduces there's only these b plus 1 possible outcomes. And so if you think about it for a little while, you'll realize that, okay, that means that this is going to take me at least log of n plus 1. So there will be at least one outcome that means log of n plus 1 divided by log of b plus 1 ios. Okay. Log of n plus 1 because that's the number of possible outcomes of the entire search, and log of b plus 1 because b plus 1 is the number of possible outcomes from what that you get when you read one block and compare everything to what you're searching for. This is basically the same thing that happens in the normal comparison-based case, but instead of b plus 1 here, you have 2, right? Because when you do a comparison, there's only 2 possible outcomes. All right, so the best we could hope for is this. And that's true just for the search operation. I don't care about adding and removing. We still, even if all I want to do is store n numbers so that I can search for them, search for a particular number, we're going to need at least this many input-output operations. All right. So if we go back to our picture, our abstract picture of a binary search tree. So actually the height here, something like log of n plus 1. And we want to somehow organize things so that we can get, we can store this binary search tree on disk so that we can get a search time, a number of blocks accessed, which is like log of n plus 1 divided by log of b plus 1. So any idea how we can do that?
Could we take potentially like the nodes that are closest to the root, like the first like B nodes closest to the root,
Mm-hmm.
and then build a tree on that one and store that in one block? And
Yeah.
then for each of the children, recurse on each of the children that come from removing that tree?
Yeah, exactly. So if you take roughly the first log base or log of B, log base 2 of B levels here of the tree, then you have about, a total of B nodes in those first log of B levels. So there are B nodes here. And attached to those things are, B plus 1. So I'm being very, very rough here because we're not really going to do it this way. There's B plus 1 trees whose height is log n minus whatever this log of B here. Okay. So I could take all these B nodes and store them in one block. And, in addition to that, so let's say those values are x1, x2, up to xb. In addition to that, I have another block that stores b plus 1 pointers or locations on disk where, the ith location tells you if I'm between xi and xi plus 1, then where's the root of the subtree that I should search, where I should continue my search. And back over in this picture, that basically says, okay, this whole top part here, the information that's in it, you can store using these 2 blocks, each of size about B. So with a constant number of IOs, you can navigate the first log B levels of this tree, and then you can keep doing the same thing recursively. So what you've really done is, you imagine splitting your tree up into levels with the distances of log B between them, or if you like, that's the same thing as cutting your tree up into subtrees, each of which has about B values. And do you know the name of this data structure? Anyone heard of this before? It's about, 50 years old.
Tyler put it in chat already, but a B tree.
Yeah, so it's a B tree. So that's why it's called the B tree. That's why B is universally the block size in these external memory models. B trees are incredibly useful, used in databases, file systems, all kinds of stuff. Even the fastest non-external things, so internal memory search structures, comparison-based search structures are actually B trees. So it's a really useful thing, worth looking at in a bit more detail. So what I just described here is the simplest version where you're given a set of n values that are ordered so they can be sorted, and you want to store them for searching. That you can do really tidily, and they don't change. You don't add or remove. That you can do really tidily by just storing the first B of them in a block like this, what I said here about keeping an array of pointers, you don't actually need, because you use this convention that the first B of these things are in a block. And if you happen to be smaller than all of them, then the next block you should look in is the block that comes immediately after this one. If you happen to be smaller, larger than x1, but smaller than the rest, then you should look in here. So those pointers are, and so on. So in the same way that you can lay out a binary tree, like when you do a binary heap, you lay out a binary tree level by level. You can do the same thing with a B tree. So nobody has to remember pointers to their parents or children, as long as it's a perfectly balanced one. And that's why I wasn't fussy about this log B here, because you don't really make a binary tree and then cut it into levels like this. You just use B plus 1 is the branching factor. B is the number of things you can store in block. All right. And what if you want to do more than that? What if you want to add and remove things? Well, that I think we've even seen an example of this in this course, something that's very close to this. Yeah, in fact, we saw a concrete example. Does anybody know, at some point very early in the course, we looked at something called a queep, and it used internally a kind of B tree. Anybody remember what it was? No. So we've seen 2-4 trees. What are 2-4 trees? These were these trees where a node stores either one value or it stores 2 values or it stores 3 values. In this case, if it has 1 value, it has 2 children. If it has 2 values, it has 3 children. And if it has 3 values, it has 4 children. And this is actually just a special case of a more general thing, which is also called a B tree. Sometimes a B plus tree, sometimes called a B star tree. There's many different variations depending on what they exactly what's going on. But these are things that store each node stores at least B over 2 values and at most let's say, I don't know, 2b or 2b minus 1 values. Right, so here, if I take b equals 2, then each node stores at least 1 value and at most 3 values. But you can imagine doing this for whatever arbitrarily large values of b, right? You know, b could be 4,000, in which case you can have things that store as you know, each node stores as little as 2,000 values, or as most as much as 8,000 minus 1 values. All right, and well, how do these work? Well, assuming you have a B tree with well, so let's write down the two rules. So this is how much they store, and you know, a node with k values has k plus 1 children. So that means there's between b over 2 plus 1 and 2b children of each node, and all leaves have the same depth. Okay, and you may have one, if you're paying attention and you're fussy about these things, you'll realize, okay, there's this case where this is not possible, and that is the case where if you have fewer than b over 2 values, then you can't really do this. But that's sort of easy. If you have so few things to store that they all fit into half a block, you just store them in that half a block. So that's kind of a boring edge case. But you know, if n is big, meaning that it doesn't all fit in one block, then these are the rules that you have to follow. And well, you know, you can see if you look at the root of this tree, it has at least b over 2 plus 1 children, right? Because it has at least b over 2 values. So there's at least b over 2 plus 1 nodes at this level, or children at this level. Each of those has at least b over 2 plus 1 children. So at the second level, there's at least this number squared, and so on, until you reach the height of the tree, which is and so at the bottom level, h, you have b over 2 plus, at least b over 2 plus 1 to the h leaves. And while you should not have more leaves in your tree than you have data in your tree, which means that n has to be bigger than or equal to b over 2 plus 1 to the h. And if you rewrite that or take logarithms, you'll get log n divided by log b over 2 plus 1 is bigger than or equal to h. Or another way of looking at that is the height of the tree is less than or equal to log n divided by something that looks like log b. In fact, this is at least log b minus 1. Okay. So you get a tree whose height is, you know, about log n divided by log b. What we were searching for, what we were hoping for. How do you maintain this? I mean, how do you add and remove things from this tree? Well, we've kind of seen it before. When I want to, let's say, add something to this tree, I search for it, and I find some leaf node, I shouldn't say it has children, with some values in it, and the thing that I want to add fits somewhere in that leaf node. So it's, you know, it fits, it should go in this leaf node. And the vast majority of time, that leaf node stores less than b values, right? So I said, or less than b minus 1 values, in which case you just take the thing that you want to insert and you put it in there. Okay. So it's a one search, and then you take the thing you want to insert and you stick it in there. Okay, but what if in that one odd instance you happen to want to insert this thing, and you get to this node and it has exactly b minus 1 values in it? Oh, sorry, no, sorry. It has exactly 2 b minus 1 values in it. That's what it means for a node to be full. All right, well, what should you do then? Well, you take this node, you split it into 2 nodes. So there used to be 2 b minus 1 values in it. You added 1 extra value, so now you have exactly 2 b values. So you can split this into 2 nodes, each of size exactly b. And where this parent used to have 1 child, you put in 2 children there. And now the danger maybe is that well, now maybe this parent has too many children, in which case you may have to split it and so on. And that splitting might happen all the way up to the root, and if you end up splitting the root, then I forgot to say one thing. Every node except the root. So. The root has bigger than or equal to 2 children. Every other node has somewhere between b over 2 to 2 b minus 1 children values. Let's say bigger than or equal to 1 value. So I think for most of you, this is not a new data structure, so we won't bother too much with all the details here. It's just you give yourself lots of room in these nodes, between b over 2 and 2 b minus 1 values. Most of the time, you want to add something, you just stick it in at the bottom, because most of the time the node is not completely full. If it is, you split it, and the splits may work their way up the tree. When it's time to remove something, similar thing happens. Most of the time you find it in a leaf, and you remove it, and nothing unusual happens. The only time that there's a problem is when the leaf that you remove it from has exactly b over 2 values in it, in which case you need to do something. And that something that you do is you either borrow from one of your neighbors, or if you can't borrow from a neighbor, that's because both of you have only b over 2 values, in which case you can merge those 2 neighbors into one thing of size b. And again, that may propagate up the tree. So all that to say is that B trees support add, remove, and search in O of log base V of n IOs per operation. And why this weird looking thing? remember, that's the same thing as writing log n over log base b of n is just log n over log b with a common base in both logarithms. And right, so the why this number? Well, because the height of the tree is at most log n over this log b minus 1. Okay. All right, that was easy. So let's make the game harder. There is another version of the external memory model called the cache-oblivious model. And at first, that model looks like you're just making, it was just invented to make life harder for us, for no good, with no obvious benefit. So in short, the definition of the model is, it's the external memory model but no one tells you the value of b. So now you might ask, why bother with this? Why is this an interesting thing to study? Well, if no one tells you the value of b, and you don't have any way to figure it out, that means you have to design a data structure that's going to work for, well, no matter what the value of b is, or at least for any reasonable range of values of b that you might encounter. So unlike B trees that are really tailored to a specific value, right? You tell me the value of B, I tell you what the tree looks like. In fact, I tell you how many children each node is allowed to have, both upper and lower bounds. But if you don't tell me the value of B, I can't even begin to make a B tree for it. So why would we want to do that? Well, that picture that I drew of the external memory model was really an oversimplification. If you look at what a computer really looks like, you have a CPU. You have a memory. In reality, the CPU does not read directly from the memory. You have a cache in between those two things. So when the CPU says, I want some memory location, some word of memory X, what happens is a whole block of memory gets read into something in the cache called a cache line. And the size of that thing is called the cache line size. So there's a value b, let's say b1, which is the cache line size. So when if the CPU asks for something from memory, one byte of data, what happens is the whole cache line of size b gets read. And it gets worse, it's more complicated than that. There's not just one cache. There's usually three. So CPU asks for a byte of memory, it gets read into the L1 cache. There's a particular block size for the L1 cache. Some portion of that gets read into the L2 cache. There may be a different block size for that. Some portion of that gets read into the L1 cache, and then the CPU has quick access to it. And it gets read into a register in the CPU. And this is just now what we think of as the internal memory model. We haven't even talked about stuff that lives on disk. From disk, you have to read a disk block into memory. If you want something in that disk block, it goes to the L1 cache, L2, L, and so on, all the way up to here. And the disk block size is different than the cache line size for L3 cache, which may be different than the cache line size for L2, which may be different than the cache line size for L1, which is definitely different than the register width of your CPU. And today, the data that you want may not even be living on the disk that's inside your computer. It may be living off in the cloud somewhere. So when you ask for a particular piece of data, a whole chunk of stuff comes across the network. How much of that, how big that stuff is, depends on the protocol for sharing, for getting things off of this cloud. But it's probably also bigger than well, it should be bigger than the disk block size, because retrieving stuff over a network is much slower than pulling it off of a local hard disk. Okay. So the reason for not telling you the value of B is that really, in any computer system like this, there are many values of B, all of them happening at once. So if you design a data structure that can work efficiently without knowing the value of B, well, that means that it works for many values of B, and in particular, it works as well as it can for every value of B in this cache hierarchy. So, if this is B5, the size of this thing, then I should be able to search. The number of cloud accesses when I search should be something like order log n divided by log B5. The number of disk accesses, if this block size on the disk is B4, well, then the number of disk accesses should be log n over log of B4. And the number of transfers from memory to L3 cache should be log n over log B3. All of that happening somehow invisibly without you even thinking about it, as long as you make one of these cache-oblivious data structures. All right. Is it clear what the justification is, hopefully? I mean, I don't want to have to make a data structure which is specifically designed for these 5 levels of memory hierarchy, with each block size pre-coded. I would like to make just a normal data structure that manages, it just works for all of them for free. Okay. So really, the model in this cache-oblivious model simplifies down to you have a CPU, you have a memory, you have a cache. I don't know. Well, I won't worry too much about how big this cache is. For us, it's not going to be important. For some other things, it matters. But basically, your CPU blindly asks for some location in memory, and your program gets the value that it asks for. But behind the scenes, that whole block of things moves into the cache. And if your CPU happens to ask for things that are in the same block, then afterwards, then you do not pay this IO for getting this thing from memory again. Okay. So of course the difficulty is you don't know how big the block is and exactly how it's aligned and so on. So you should be able to do this so that it works no matter how big the block size. All right. So how are we going to manage that? Well, let's go back to where we started. So we started with a binary search. So let's just think about this cache-oblivious model. We don't know the block size. We want to do just searching in a sorted set. And we want this to be somehow as fast as possible. And we saw that one way to think about this when we knew the block size was we would take a binary search tree and chop it up into layers. Each layer had height log of b, which meant that each little subtree between two layers had about b values in it. Now we would like to do the same thing, but without knowing the value of b. Okay. So for all we know, b could be as big as n, or b could be as little as 20, or log n, or square root n, whatever you want to know. Okay. So let's start with the sort of simplest thing. So here's two possibilities. B equals n, or b equals square root n. So in this case, if we want to be sort of optimal in this case, then we should be able to answer our questions in log n divided by log b. But if b equals n, this is just 1. So if all of our data fits into one block, then yeah, indeed, we should be able to answer any query we want just by reading one block. Now, if b is square root n, then we should be able to answer things in log n divided by log b. Well, what's log n divided by log b? Log n, log n divided by log of square root n. What's the log of square root n? It's 1/2 log n. So actually, if we drop the O for now, just so we can see what's happening. This is log n divided by 1/2 log n. The log n's cancel out, the 1/2 inverts, so that's 2. So if b equals n, we should somehow be able to do it in 1 IO. Yeah, that seems feasible. And if b is equal to square root n, we should be able to do it with 2 IOs. Does that seem feasible? So if you knew b was the square root of n, can you give me a data structure that will, so I can hold square root n elements in one, retrieve square root n elements in one disk access. Can you give me a data structure that works in 2 disk accesses?
Right now, we know the value of b right now.
So you know the value of b right now.
So why we are not using the previous one? Like the one you draw in there.
Okay. So we use a B tree with b equals square root of n. And in this picture, that looks like, we take the top of our tree, so we have square root n values up here, and then attached to each node here is a bunch of trees, each of which has size square root n. Or in terms of B trees, there's one block that contains all this, there's another block that contains this, another one that contains this, and so on. You read the first block, and you know which of these second blocks contain your answer. So that's the 2-block answer. But notice that this is only 2 IOs, so even if b was n, this would still be a good solution for b equals n. Maybe it does it in 2 IOs, and it could have done it in 1, but I mean 1 and 2, that's only a factor of 2 difference. So somehow we cannot have to worry about the case when b equals n, just we'll settle for solving the case b is square root of n, and that's only a factor of 2 off from the case when b equals n, or anything in between. So as soon as you're bigger than square root of n, well, the answer is going to be somewhere between 2 and 1. So if I can do it in 2, that's great. Okay. All right. So let's think about that. So that seems to suggest a good starting point is to have a data structure that's going to go into memory like this. Let's call this A, and let's call this A1, A2, A3, up to a square root n. The contents of A will go first, and then A1, A2, and so on, up to a square root n. And if my block size is anywhere between square root n and n, then, well, when I look in A, I will read all of A. So if I look at even one thing in A, I'll read all of it. That'll be enough to get me through this first top half of the tree. From there, I will need to look into one of these things. And one of those things, if my block size is, so I'll need to look, maybe in this one over here. And if my block size is at least square root n, that means this thing fits into at most 2 blocks. Right? So a block is big enough to store all of this, but maybe this thing isn't aligned perfectly with the way the blocks are aligned on disks. So it might span 2 blocks, but it's at most 2 blocks. All right. Good. So notice now that I have not said anything. So all I've told you is the top part of the tree, we'll put that first, and then we'll put these other parts of the tree here in this order. You can say like each of these things consecutive. I haven't told you what order we should store the top part of the tree in. Any suggestions?
Could we recurse on the top part of the tree?
Mm-hmm. So basically what I said, or what I've done is, well, said the way to do a tree of size n is to have, the way to make a data structure of size n is to make a data structure of size root n, which will then push you into one of these other data structures of size root n. Well, then to make a data structure of size square root of n, maybe what I should do is make a data structure of size the square root of the square root of n, which is n to the 1/4, which will then push me into exactly one of these substructures, also of size n to the 1/4. And in terms of my memory layout here, right, that means I'll have this guy. So I don't know, maybe that's called A0. And this one is A01, A02, A03, all the way up to A0 n to the 1/4. Okay. All right. Great. And well, this was me trying to solve the problem on something of size square root of n. I have a whole bunch of problems of size square root of n that I want to solve. So I'll do the same thing to each of these. So the big picture of the memory layout doesn't change. All I'm doing now is explaining to you inside one of those big things, these square root n things, what does that look like inside of it? Well, the stuff closest to the root gets put in at the beginning. So the first half levels of this tree get put in at the beginning. After that come the subtrees in this order. And I still haven't totally specified the ordering of elements here yet. All I've told you is that the first n to the quarter elements go here, and then this subtree of n to the quarter elements goes here, and so on. But I still need to specify the order of the elements inside this tree. And for that, I do the same thing. I recurse again. So there'll be a top tree of size n to the 1/8. And a whole n to the 1/8 subtrees, each of size n to the 1/8. So that breaks this down into even finer level of detail. And the recursion ends when I get down to like a subtree of size 1. Okay. All right. So the claim is that this thing, no matter what the value of b, or at least as long as b is not much bigger than n, again, b being much bigger than n, it doesn't really make sense in the following sense. So as soon as b is as big as n, This says you should be able to do it in a constant number of blocks by reading a constant number of blocks. And you know, if B is way bigger than N, you're still going to have to read at least one block. So, so that doesn't really make sense to assume that B is much bigger than N. As long as when B is about N, we can do it in a constant number of blocks. Yeah, so the claim is that for any value of B between N and between, let's say, in fact, even 1 and N, that this searching in this particular tree will take O of log N over log B IOs. Okay. So we kind of have an idea how that's going to be, or what that's going to look like, or some idea of why that should work. For instance, we already checked that this will work if you take B to be bigger than square root of N but less than N. We already figured out that in that case, you'll have to look at this block and then one other subtree of size square root N, which is going across at most 2 blocks if the block sizes are bigger than square root N. So we just need to generalize that to any value of B. And, well, we can do that because somewhere along the way, we're going to hit a value of a tree size here. So we're going to hit something like a K where B is less than or equal to N to the 1 over 2 to the K, but it's bigger than or equal to N to the 1 over 2 to the K plus 1. So for example, maybe the block size is between N to the 1/8 and N to the 1/4 in this picture, right? That's what this looks like. Okay. So when that happens, we don't know it, but I mean, it does happen somewhere in this range, right? Because we start at N and we go all the way down to 1. So there's going to be some value of K for which this is true, and we're going to have something in our structure is going to do this. So if we look at, even though we don't know it, behind the scenes, the memory management system is taking care of this for us. When we do a search in the binary tree, it starts at the root tree, which has this size, which is it is less than N to the 1 over 2 to the K plus 1. And that goes, that searches through those first levels, and then goes to another one that's attached there, and to another one, and to another one, and to another one. So these, in my decomposition of my tree, these are things that are consecutive in memory. Okay. So each of these things goes off to some consecutive location in memory, like this one here. Well, we know actually it goes right to the beginning. This one here, I'm not sure, it goes somewhere. but its size is, well, its size is not bigger than B, so it's not bigger than the block size of my, whatever, my disk, if you want to call it that, which means that, well, that means it's split across at most 2 disk blocks. Right? So it could fit into 1 disk block, but because it's not necessarily aligned with the disk block, it's split across maybe 2 of them. But at most 2, because the disk blocks are bigger than the size of this thing. All right, so for each of these trees that my search goes through, there are 2 disk blocks that contain all the values in this tree. So when I look at the first thing in this subtree, that causes a disk block to get retrieved. And then I can search in this tree as long as I'm only in those, in that disk block. And in fact, everything along this path will be in at most 2 disk blocks. Okay? So for each of these subtrees, I have to possibly retrieve 2 blocks from the disk, or from the cloud, or from the cache, or whatever this part of the memory hierarchy I'm looking at is. So really, the number of IOs is just the number of these trees that my search goes through. Okay. All right. So this is something. This has a size into, let's call this B prime. So what can you tell me about B prime? Well, I know that B prime, that's this guy, is smaller than or equal to B. But if this is B prime, then this is B prime squared. If I take this, well, if I take this and square it, that becomes n to the 2 over 2 to the k plus 1, which is just n to the 1 over 2 to the k. So the sizes of these trees, they're all smaller than or equal to b, but they're also less than or equal to b squared. Or sorry, they're all, yeah, if you square them, they're bigger than b. All right, but then that means that the log of b prime is less than or equal to the log of b is less than or equal to 2 times the log of b prime. And now we're basically done. So what did we have to do? Number of these trees here is the length of this search path, which is log n, divided by the height of one of these trees. The height of one of these trees is a log of b prime, because they're trees that store b prime values, but the log of b prime is at most, is at least, so let's divide by 2 everywhere, so I take a half here, that stays there, stays a half, so that thing is bigger than or equal to 1/2 log of b, so that's less than or equal to so we get 2 log n over log b. Okay. So the point is that even without knowing the value of B, we can kind of make a guess about it. And our guess does not have to be accurate at all. As long as the guess is within, it's not even within a factor of 2, but it's within a factor of, a square, then because we're taking logarithms, it's close enough. So just in the same way that whether the block size is as small as root n or as big as n, does it really make much of a difference? The difference is between 1 and 2. The same thing happens everywhere for every value of b. And we nicely have a way of decomposing a tree this way, recursively, in starting with the root n top, also laid out recursively in these things. And this is a layout of a completely balanced binary search tree into an array, and it has a name, and the name is the Van Em-de-Boas layout. Why is it called the Van Em-de-Boas layout? Oh, maybe it starts to look a little bit familiar now. Remember the Van Em-de-Boas structure had this top layer of size square root the size of the universe, kind of like this does. Attached to it were just as many structures, all of the same size. And how did you navigate the top layer? Well, you recursively built the Van Em-de-Boas structure just for the top layer. And the same thing happens recursively. So this idea, even though it appeared only in the last, in terms of external memory data structures, even though it, as Van Em-de-Boas layout only shows up in the last 20 years in the context of cache-oblivious, really it's the same, basically the same idea Van Em-de-Boas had in the 1970s in a completely different context. So it's an important idea. Okay, so next class, we will look at making this dynamic so that you can add and remove values. So all I've shown you here is if you give me the set of n values, how do you lay them out?
Yeah.
But what if the values?
Who's speaking?
Yeah.
بله سلام. مرسی شما. بله خوب هستین. مرسی آقای معتز.
Okay. All right, so that's a good place to end it today.
خیلی ممنون. مرسی.
Do you have any questions for me? No? All right. Okay, so then I will see you on Thursday. Bye.